As many of you know, Elizabeth Dole was the head of the American Red Cross, is a former cabinet member in the Reagan administration, and is the wife of former Republican presidential candidate Robert Dole. She has an engaging personality and is a well-known political figure. At the 1996 Republican National Convention, she gave a speech on behalf of her husband. This speech was part of a well-planned campaign strategy. Why? Well, the Dole campaign knew from its polls that something called the gender gap was affecting his campaign. Senator Dole was trailing Democratic candidate Bill Clinton in the polls generally, but with women voters, his support lagged even further behind. If he were going to win, Senator Dole would have to find a way to appeal to women voters and close the gender gap. Clearly, Elizabeth Dole and other prominent Republican women were part of that effort. In this program, we will investigate the gender gap and show how political scientists or political practitioners, such as the Dole campaign strategists, use statistics and empirical data to learn about the political world. We will introduce some new applications as well as review some things you already know, reading a frequency table, reading a two-way table, and using chi-square as a test of significance. Our purpose is to show how political scientists use data and statistics to learn about events in the political world. Political scientists are interested in a variety of questions dealing with voting. Who's most likely to vote? Are citizens who vote different from citizens who don't vote? What issues are most important to voters? How do voters decide which candidate to vote for? One issue that has been of interest is the gender gap. The gender gap is a term that has been used to describe the apparent differences in how men and women view political issues and which candidates they vote for. When political scientists refer to the gender gap, they usually mean that, as a group, women voters are more likely to vote than men for Democratic candidates. This phenomenon was first noticed in presidential elections during the 1980s and has been widely discussed by journalists and political scientists since then. But do women and men actually vote differently? It would not be uncommon in the study of politics to find that some widely held common knowledge is not really supported by reliable data. Perhaps when we actually look at how men and women vote, we'll find that they act in pretty much the same way. That result would surely not support the notion of a gender gap. Of course, if we found evidence that men and women do have different political preferences, that information would be of interest not only to political scientists and pollsters, but also to politicians seeking office, their campaign advisors, and other people trying to influence who gets elected to office. So, we can use statistical methods and survey data to try to find the answer to this question. Let's start by stating a research hypothesis. This is a statement about what we expect to find when we look at empirical evidence. And in this case, our hypothesis comes from the theory that there is a gender gap. So our research hypothesis is, women are more likely than men to vote for a Democratic candidate in presidential elections. In our research hypothesis, we stated that gender affects how people vote. So we collect observations on two variables, gender and vote choice. Gender is our independent variable, vote choice our dependent variable. While our research hypothesis makes our expectations clear, it is not a statement that we can use directly in significance testing. For a statistical test, we need a null hypothesis. A null hypothesis, as you recall, is simply a statement that there is no relationship between the variables of our research hypothesis. From the information about our variables, it is easy to state our null hypothesis. The null hypothesis is that there is no relationship between gender and vote choice among American voters. Now that we have identified our hypotheses, we can look at the empirical data. In order to test our hypothesis, we need empirical data that will allow us to compare how women and men vote. We could, of course, design a questionnaire, select a sample, and go out and interview people about how they have voted. Fortunately, we don't need to do a survey ourselves because there are several excellent surveys that have already been collected. We will use data from the 1996 American National Election Study. These data were gathered during the 1996 presidential election. This 1996 survey continues a long series of election studies that have been conducted during every presidential election since 1952. The National Election Study uses a probability sample to select respondents so that the results are broadly representative of all eligible Americans. Once people have agreed to be interviewed, they are asked a long list of questions about their interest in politics, their views of the candidates, their positions on political issues, even which TV shows they watch. The people who were interviewed, the respondents, were interviewed twice, once before the election and once after the election. In 1996, more than 1,700 people completed the post-election interview. Over the years, political scientists have learned a lot about what Americans think of politics and elections from the National Election Studies. Let's look at the data on how people reported voting in the 1996 elections. This frequency table shows how people reported voting in the interviews conducted shortly after the election in November. The responses have been grouped into 5 categories: those who reported voting for Democratic candidate Bill Clinton, those voting for Republican Bob Dole, those voting for Reform Party candidate Ross Perot, people voting for other minor party candidates, and those who did not vote in the 1996 presidential election. This graph shows the absolute number of people who gave a certain response, as well as the relative frequency or percentage. This graph also shows what is called the valid percent. As you can see, the valid percentages are different. The relative frequency is calculated based on all 1,714 respondents, while the valid percent is calculated by using only the 1,134 number of people who reported voting in 1996. As always, when working with percentages, it is important to know how a particular percentage is calculated. Let's look at the number of respondents who voted for Bill Clinton as an example. The absolute number of people in the national sample who reported voting for Clinton is 600. When we divide that number by the total number of people in the sample, we see that 35% of all people interviewed voted for Clinton. That percentage, however, includes everyone in the sample, even those who did not vote. If we exclude non-voters, we have only 1,134 valid cases. That's where the term valid percent comes from. Using the number of valid cases, 1,134, as the divisor, we see that 52.9% of the people in our sample who reported voting in 1996 voted for the Democratic candidate. At this point, it might be useful to remember that we are dealing here with a sample of American citizens. We know from the national vote totals that President Clinton received only 49% of the total votes cast. In our sample, however, nearly 53% of the respondents reported voting for Bill Clinton. The difference between the 49% of all American voters who voted for Bill Clinton and the 53% reported in our survey is what is commonly known as sampling error. Sampling error is the small amount of error that can occur when using a sample to estimate a characteristic of a population rather than measuring the whole population. Of course, the advantage of using survey data is that we can learn much more about people than we could using only the national vote totals. We have now seen how people reported voting in 1996. But our original question was, do women and men vote differently? We can find the answer to our question by looking at a two-way table. In political science, two-way tables are more commonly called crosstabulations, or just crosstabs for short. Whichever name we use, the purpose is the same. The crosstab or two-way table is one way to show the relationship between two variables. This graph compares how women and men reported voting in our sample. For simplicity, this graph shows only percentages, and it excludes respondents who did not vote. We can see that women voters in our sample were more likely to vote for the Democratic candidate than were men. As the graph shows, 59% of women reported voting for the Democrat compared to 46% of men. Only 33% of women reported voting for the Republican, while 44% of men did so. The graph also suggests that men were slightly more likely to vote for Ross Perot. We can show this comparison a bit more easily by calculating differences. This graph shows the percentage differences between women and men, with a positive sign indicating more support among women and a negative sign, more support from men. Clearly, our sample data supports the gender gap hypothesis. 13% more women reported voting for the Democrat, while 11% more men voted Republican. So the National Election Study data shows a gender gap. That settles it, right? Well, not so fast. Remember, our sample has only about 1,000 voters, so what we know is that there was a difference in the voting patterns of women and men in the sample, and what we really wanted to know was whether there is a gender gap among all voters. What we need to know are statistics that will help us to move from what we can observe directly in our sample data to statements that are likely to be true of the entire population of American voters. Since the National Election Study data was originally collected using a probability sample, we can use the information we have from our sample to decide whether the sample results are likely to apply to the population of American voters. To put it bluntly, whether as a political scientist or as a campaign consultant, we aren't interested in the people in the sample for their own sake. We are, however, interested in using the information from the sample to infer what the population of all voters is like. In order to use statistics, we will need a bit more information than our original graph contained. Let's look at a cross-tabulation with more information. This graph shows the same percentages as before, but it contains some important additional information. One addition is that along with the percentages, this graph also shows the absolute frequencies. A second addition is the marginal entries that combine all the numbers in a column or row. In fact, this crosstab consists of two parts: the cells of the table and the marginals. The columns, labeled women and men, and the rows, labeled Democrat, Republican, Reform, and other, define the crosstab cells. For example, in the Democrat women cell, we can see 360 voters who said they voted for Bill Clinton. That's 59% of women voters. The last column and the last row, labeled total, are called the marginals. We see that a total of 600 men and women in our sample voted for Bill Clinton, while 434 voted Republican. Along the other margin, we find 611 women, adding together Democrat and Republican voters, and 523 male voters. Finally, there were 82 supporters of Ross Perot and 18 people who voted for other minor parties. Adding up either the column marginals or the rows, we get a total count of 1,134 voters. As with each of the cells, the marginals contain both absolute frequencies and the percentages. We now have the information we need to proceed. With this information, we can conduct a chi-square test. The chi-square test is valuable because it allows us to determine whether the results observed in our sample are strong enough to justify inferences about the population of voters. Before we review the mechanics of the chi-square test, however, it is important to emphasize that use of the chi-square is based upon the assumption that we are dealing with data collected using a probability sample. The term probability sample simply means a sampling strategy in which the probability of any particular respondent being chosen is known. An example of a probability sample is a simple random sample. Let's say you had a population of 100 people and you wanted to select 10 of those people to interview. If you used a simple random sample, say by giving each person a number and then using a table of random numbers to pick 10 numbers, the probability of any one person being selected would be 10 out of 100, or 10%. And the probability for every person in the population would be the same. Knowing how the sample was chosen allows us to use some statistical assumptions about how well a sample represents the population. If the data being examined are not from a probability sample, however, then a key assumption of the chi-square test has not been met, and the results will be meaningless, or worse, misleading. Fortunately, the calculations for a chi-square test aren't difficult. As this formula shows, the chi-square statistic can be found by taking the observed frequency for each cell, subtracting the expected frequency, squaring the difference, and dividing by the expected frequency. By adding the numbers for each cell together, we get the chi-square statistic for the table. The first thing we need to know is the expected frequency. The expected frequencies are the number of cases that we would expect to see in the cell if the null hypothesis is true. Remember the null hypothesis? It asserts that men and women vote in the same way. If true, we would expect the frequency for any cell in the table to be the result only of the total vote counts and the number of men and women who voted. The larger the difference between the expected frequencies and the observed frequencies, the more confident we will be that the gender gap observed in our sample did not occur by chance. Since there are 8 cells in our graph, we have to calculate 8 expected frequencies. We do this by taking the row marginal, multiplying it by the column marginal, and dividing by the total number of cases. Let's look at the calculations for the first cell. From the marginal frequencies, we know that 600 people in the sample voted for the Democrat, and there were 611 voters who are women. When we multiply these two numbers together and divide by the total number of respondents, 1,134, we get 323, rounded to the whole number. That number is the expected frequency. Now what does that tell us? It says that we expect 323 female votes for Bill Clinton in the absence of a gender gap. From our original graph, we know that 360 women reported voting for Clinton. So when we compare this with the 360 women who actually voted for Clinton, we see that the number of observed cases is greater than the number we would have expected. Here are the calculations for all the expected frequencies for the 8 cells of our graph. Notice that the larger the marginal frequencies are, the larger the number of expected cases. With our expected frequencies, we can now calculate the chi-square test statistic for our graph. Again, we have one chi-square entry in each cell. Let's look at the calculation for just one cell. The calculations can be done in 3 steps. The observed value, the actual number of women who reported voting for Clinton, is 360. The expected frequency is 323. In step 1, we subtract the observed from the expected and get 37. In step 2, we square that number and get 1369. In step 3, we divide the squared term, 1369, by the expected value, 323, to get 4.2. This number, 4.2, is the chi-square entry for the first cell. Here are the chi-square entries for all 8 of the cells. After we calculate the value for each cell, we sum those values to arrive at the chi-square statistic for the graph. This number is 20.8. So the observed chi-square is 20.8. What does that mean? Well, as with any test of significance, the meaning of the chi-square number becomes more relevant when we compare it to a critical value of the chi-square distribution. The chi-square statistic is a random variable that has a standard distribution as long as the null hypothesis is correct. A critical value for this distribution can be found in a table at the back of your textbook. To find the critical value, we need 2 pieces of information. First, we need to know the significance level, often called alpha. As you should know by now, the alpha level is the probability of committing a type 1 error. That is, the probability of rejecting a null hypothesis as false based on the sample data when it is in fact true in the population. Since we want to minimize this kind of error, we typically select a low value for alpha. Indeed, simply by convention, most social scientists identify 0.05, that is a 5% probability of making a type 1 error, as an acceptable alpha level for significance tests. Next, we need to know the degrees of freedom. The degrees of freedom for any table can be found by this formula: the number of rows minus 1 times the number of columns minus 1. For our graph, that's 4 rows minus 1, which is 3, times 2 columns minus 1, which is 1. So 3 times 1 equals 3. Now that we have identified our alpha level and degrees of freedom, we can locate the critical value from any standard table of chi-square values. With an alpha level equal to 0.05 and 3 degrees of freedom, the critical chi-square value is 7.8. This chi-square random variable can have any value from 0 to positive infinity, but all values are not equally likely. Values equal to or greater than 7.8 will occur only 5% of the time. With the observed chi-square value, 20.8, and the critical chi-square value, 7.8, we can now make a decision about our null hypothesis. Formally, the decision rule is, if the observed chi-square is greater than the critical chi-square, reject the null hypothesis. If the observed chi-square is smaller than the critical chi-square, we fail to reject the null. In this case, the observed chi-square of 20.8 is larger than our critical chi-square of 7.8. Based on our decision rule, we can reject the null hypothesis at a 5% significance level or a 95% confidence level. So we have rejected the null hypothesis. What does that tell us? Keep in mind that the null hypothesis is a statement about the lack of a relationship between gender and voting in the population of all voters. Based upon the relationship observed in our sample data, we are 95% confident that the hypothesis of no relationship between gender and voting is false for the population. More importantly, by rejecting the null hypothesis, we have indirect confirmation for our research hypothesis. Remember that our research hypothesis is that women voters are more likely than men to vote for a Democrat for president. Though for logical reasons we cannot claim that our research hypothesis is proven to be true by our evidence, we can say that our evidence is consistent with our research hypothesis. As you just saw, the results of this chi-square test led us to reject the null hypothesis. But let's take just a moment to consider what would happen if we could not reject the null hypothesis. Suppose that rather than 20.8, the observed chi-square statistic is 6, and our critical value remains at 7.8. Then we would have reached the opposite conclusion. Following our significance testing steps, we must fail to reject the null hypothesis. Why in this hypothetical example did we fail to reject the null? Because with a test statistic of 6, the probability of making a type 1 error is now greater than 5%. And most social scientists would agree that when the probability of rejecting the null hypothesis becomes greater than 5%, we should be cautious about rejecting the null. What then can we conclude if hypothetically we fail to reject the null? Well, in practical terms, we say that any observed differences between men and women in the sample are inconclusive. We simply have not found evidence to support our hypothesis that there really is a difference between men and women in the population. Now that we have talked about what happens when we can't reject the null, let's return to the real results and consider how to proceed. The empirical data we observed from the 1996 national election study indicates that women voters are more likely than men to vote for a Democrat. A significance test allowed us to rule out the possibility that the relationship we observe is due to having used a sample of voters rather than the entire population. Based upon what we have learned, we can be reasonably confident in the view that there is a gender gap among American voters. So we have evidence to indicate there really is a gender gap. Another question we might want to ask at this point would be, how strong is the relationship between gender and vote choice? As you should recall, the correlation coefficient can be used to describe the strength of a relationship between two variables. However, the usual correlation assumes that both variables are measured on a continuous scale. The variables in which we are interested, gender and vote choice, are not continuous variables. They are categorical variables. Gender and vote choice are examples of a particular type of categorical variable known as nominal variables. The word nominal means name. Such variables are classified by names, but cannot be rank ordered. The same is true of our other variable, vote choice. As with gender, we can distinguish between voting for a Democrat or Republican by categories, but we cannot rank order these categories. So we can't use a statistic such as the correlation coefficient to measure the degree of association. However, there are other measures of association that we can apply to this type of problem. One of these is based on the chi-square test statistic we have just studied. By itself, the observed chi-square value that we calculated is not very useful as a measure of association. But the observed chi-square value can be adjusted so that it provides a measure of the strength of association on a standard scale. One statistic that does this is Kramer's V. As the formula shows, Kramer's V is calculated by dividing the observed chi-square statistic by the number of cases times k minus 1 and then taking the square root of that number. The k in this formula is simply the number of rows or columns, whichever is smaller. Kramer's V always falls between 0 and 1. A value of 0 indicates no association, while the closer the value is to 1, the stronger the association. So, for instance, a Kramer's V of 0.75 would be a fairly strong association between two variables, while a Kramer's V of 0.15 would indicate a weak association. As you may already have recognized, Kramer's V takes on a smaller range of values than does the usual correlation coefficient, which can take values between -1 and +1. Kramer's V does not take on negative values because measures of association for purely nominal data cannot indicate the direction of a relationship. They can only tell us about the magnitude of the association. So how strong is the association between gender and vote choice in our sample of 1996 voters? We can easily calculate Kramer's V from the information we already have. Again, the observed chi-square value that we calculated earlier is 20.8. The number of cases equals 1,134. Our graph has 4 rows and 2 columns, so k, the smaller of the number of rows or columns, is 2. 2 minus 1 equals 1, so we multiply our number of cases by 1. When we plug these numbers into the formula for Kramer's V, we get a value of approximately 0.14. What does that tell us? Well, 0.14 is closer to 0 than to 1, so it indicates that the association between gender and vote choice is not especially strong. There is no widespread agreement as to exactly what values of Kramer's V constitute a strong or a weak association. Although we might have expected a higher value for our Kramer's V, the magnitude of this measure actually fits fairly well with the percentage differences that we observed in the national election study data. Let's look at the graph of differences in vote choice by gender again. We see that there is a 13% difference between women and men in their vote for the Democratic candidate. But imagine if this difference were much bigger. Suppose hypothetically that 80% of women and only 30% of men voted for the Democratic candidate. That would give us a difference of 50% between women and men and indicate a much stronger relationship between gender and vote choice. Or conversely, suppose that 55% of women and 50% of men voted for the Democrat. That would be a difference of only 5%. Even a small difference, such as 5%, would be consistent with the idea of a gender gap, but it would be a weaker relationship than either a 13% difference or a 50% difference would indicate. In conclusion, we have examined how political scientists study the gender gap. First, we formulate a research hypothesis to clarify what we expect to find empirically. The national election study data allow us to conduct a formal test with a representative sample of American citizens taken in 1996. By examining the cross-tabulation between gender and vote choice using the sample data, we discovered evidence that was consistent with the idea of a gender gap. The sample data showed that women voters preferred the Democratic candidate to the Republican in 1996, despite the best efforts of Elizabeth Dole. Our statistical exploration did not end with the crosstab. Because we want to be certain that the relationship in our sample also holds in the population of all voters, we conducted a significance test. The significance test allowed us to test the null hypothesis that there was no relationship between gender and vote choice. The appropriate test was the chi-square test, a method widely used in political science and other social sciences. Based on the result from the chi-square test, we rejected the null hypothesis, concluding that it is unlikely that there was no relationship between gender and vote choice in the population of the voters in the United States. When we calculated Kramer's V, however, we found that the strength of the association between gender and vote choice was rather weak. What do these two pieces of information taken together tell us about gender gap? First, the results from our chi-square test indicate that there is a difference between the vote choices of women and men. Of course, we have to recognize that this statement will not be true for every man or woman. But in general, there was a significant difference between how women and men voted in 1996. Still, the association between gender and vote choice is not a strong one. Political scientists have long recognized that voting is a complex decision that can be influenced by many factors. Political issues, candidate image, individual partisanship, and the state of the economy, to name just a few. Thus, we would not be surprised to find that differences in gender are only weakly associated with vote choice. Of course, the study of the gender gap will not stop here. As political scientists, we will want to look to other sources of information, such as exit polls or other opinion surveys, to try to confirm our findings or look for changes. Also, we will want to control for other factors to see if other variables might be responsible for the apparent differences between women and men. And finally, we will want to look more deeply into the gender gap to see if we could determine why women and men might behave differently. Statistical methods will be just as useful in these extensions as they have been in our initial study of the gender gap. Thank you for watching.